way down to lab 7, falling objects. Hopefully you already read that supplemental information. And then if you go into the notebook, again, there's not really much going on in these notebooks anymore. They just have the links for the simulators at the top. Let me share my actual screen. So you have 2 simulators this time around. One of them is a simulation of a ball dropping to the ground, and one of them is a simulation of a coffee filter dropping to the ground. So I'm going to click on this ball one first, and it's going to bring you to this page. From here, you have to click on one of these links. If you have a Windows, you click on the Windows. If you have a Mac, you click on the Mac. I have a Windows, so I'm going to click on this one. It'll bring up the little thing that's downloading. We're going to wait a second. And then it works like half of the time for me. It brings up this blue screen of doom where it says that it doesn't recognize it. You're going to click on more info and you're going to tell it to run anyway. Honestly, it seems a little sketchy to me, but this is what we use for the class. And this is what it's going to bring up. This isn't as nice looking of a simulation as the ones that we've been using. But the idea of what you have going on here is you have a meter stick, you have a ball, a sensor at the top, and you can drop the ball from various heights. There are these plots on the right. Do not use them. If you do, it'll be very obvious and you'll get some really weird data. So don't use them. They're not accurate for what we're doing. So this is a pretty simple and straightforward simulator. You move the ball, you drop it. That's it. You pick which height you want to drop it from. What you're going to end up doing is timing how long it takes for it to fall, but again, using your own timer, not these. And that's it for the simulator. If we go into the other one, this coffee filter one, same thing, you have to click which version of your computer you have. I have a Windows. You're going to click on the tab to open it. You're going to say more info and then run anyway. And it looks almost identical. The only real difference is now your meter stick is a 2 meter stick just about. And you have this paper coffee filter instead of a ball. So if you drop the coffee filter, it falls at a different rate. Again, you can drop it from a bunch of different heights. You'll pick with your group what heights you want to drop it from. You'll drop it multiple times from each height. But this is it. Again, it's a very simple simulator compared to what we've been using. Are there questions about how these work? Okay, awesome. So the next thing I'm going to do is just pull up my notebook in OneNote. So this is, excuse me. So this is just that notebook that I just had open with the 2 simulator links at the top. And these are just the notes that I have in my discussion space. So again, this is a 3-week lab. The goal of the lab is to find the acceleration of 2 different objects and compare them to each other. We're going to do that by just dropping these 2 different objects and timing them a bunch. So we have it broken down by week. This first week, you were just purely designing your method. Just like the last lab, you're going to need 2 different methods, one for the simulator and one for real life. And work as a group. You can talk about your objective as a group, you can talk about your prediction as a group, and you can design the method as a group. And just so you have more context as to what we're going to be doing so that you can put that in your method, you're measuring the time that it takes for 2 different objects to fall to the ground from different heights. And then you're going to use some physics equation to calculate the acceleration. Now, I write acceleration, but I have gravity in parentheses. Intuitively, we want to say that it's the acceleration due to gravity, but it's actually not gravity. The ball acceleration is going to be very similar to gravity, but the coffee filter won't be. What you're actually measuring is the net acceleration. So just, I know that's a really weird fine point between the two. It's just kind of better physics moving forward to just call it acceleration. So that's what I'm going to do now. Only acceleration. I'm not going to call it gravity because it's not really gravity anymore. Are there questions about what we're doing for week 1? Okay, so next week you're doing your actual data collection. Again, collect the data with your group. Divvy up that work because you have a lot of measurements to take. You should have about 200 measurements. That's 100 for the ball and 100 for the coffee filter. And that's it. That's why this is a 3-week lab, because you were taking 4 times the amount of data that you needed to take for the last lab. Are there questions about week 2? Okay. Then week 3 is your analysis and conclusion. You will have 3 plots in total. You're going to have a plot of displacement versus time squared for the ball. You'll have a plot of displacement versus time squared for the filter. And then after, calculating the acceleration, you're going to create a whisker plot that compares the acceleration of the ball and the acceleration of the filter to each other. Only to each other. You should only have the 2 points on your whisker plot. Don't include gravity. Only the ball and the filter acceleration. The acceleration calculation that you're going to use is this equation. This displacement is equal to 1/2 AT squared. And we're going to go over that. And then, like I said, you'll compare those accelerations. So in your conclusion, you'll need to have what your final acceleration is for the ball and for the filter. And then you'll need to talk about the 2 accelerations together. Are there questions about the timeline for this lab? Okay, then let's get into some physics. Okay, so we're going to start with one of your kinematics equations. Specifically, the x final is equal to x initial plus v initial times t plus 1/2 AT squared. So this equation hopefully looks very familiar. Again, this is just one of your main kinematics equations that you've probably used many times by now. I hope you've used many times by now. So we're going to do a couple of things to this equation to make it more usable, basically. First thing we're going to do is move this x initial over so that we can just call this the change in x. Then the second thing we're going to do is get rid of this term. We can do that because we're dropping the ball in the coffee filter from rest. So this becomes 0, because that's all. When you say that something is dropped from rest, what we're really saying is that the initial velocity is 0. So what we're left with is that change in x is just equal to 1/2 at squared. We're just going to call this change in x the displacement. It's the same thing. You can also think of it as the height that you're dropping it from is just equal to 1/2 at squared. And we're going to do the same thing that we've done for the last couple of labs now. And we're going to make this look like the equation of a line. So if this looks like the equation of a line, what are my y values?
Displacement.
Displacement, exactly. What are my x values?
T squared.
T squared. This is what's a little confusing. We've been working with time squared as our y values up until now, but for this lab, they are actually your x values. So that means that everything that's left over is equal to the slope. So the slope is equal to 1/2 acceleration, or with just a little bit of algebra, acceleration is equal to 2 times your slope. And if we plot this, again, this is displacement versus time squared, we get something pretty linear. And you get a slope from this line because it's, y is equal to mx. This is the slope that you use to get this acceleration. Are there questions about how we solve for the acceleration? Okay, so the acceleration is pretty simple to solve for this time. It's not what's going to take you the longest. So when we write out our total measurement formally, we'll write out that the acceleration is equal to some value with units, of course, plus or minus some uncertainty with units, of course. We just talked about how we get our acceleration from our slope. This is what becomes our value. If we used our slope to find acceleration, what do we have to use to find the uncertainty?
Max mean.
Yep, that max-min method. So just a quick review about how we do that. You have some plot, you have some trend line, but your points all have error bars, right? I'm just going to draw the error bars themselves, maybe. Your points all have error bars to them. So you have to draw your max and your min lines. Your min line would probably look something like that, and your max line would probably look, oh, my max line's not going to look very good, actually. My trend line doesn't look very good. That's the problem. So you'll have some max line that probably looks like that. You get a slope right from your max and your min. Well, the first thing we want to do is to calculate the uncertainty in the slope. And we do that by finding the difference in those slopes and dividing by 2. And this gives us our uncertainty in the slope. But the uncertainty in the slope does not equal the uncertainty in acceleration. The relative uncertainty in the slope does equal the relative uncertainty in acceleration. So we have to use this relationship to find the uncertainty in acceleration. Just as a note, the relative uncertainty always equals the uncertainty divided by some value. So for the case of the relative uncertainty of our slope, that's just equal to the uncertainty in the slope divided by the slope. You get this uncertainty in the slope using the max-min method. You have a slope that you got from your trend line. So you know both of these numbers. Our relative uncertainty in acceleration, we can get the same way. It's just the uncertainty in the acceleration divided by acceleration. This is what you are trying to solve for. You know what acceleration is because you got that by calculating 2m. So you get that your uncertainty in the acceleration is just equal to that uncertainty in the m, the slope, divided by the slope, times by your acceleration. That is how you get this uncertainty. So you have to do both of these things to find the acceleration. And overall, the uncertainties have been looking really well in the notebooks too. But if you are still struggling with this min-max method or the calculations, please let me know. I'm more than happy to go through it with you as many times as we need so that you understand it. If you look on our announcements page on Canvas, the Lab 5 summary goes through the calculations for the uncertainty. And then there's that min-max method video also under the announcements that walks you through how to draw those lines in. Are there questions about how we find the acceleration? Okay. So then you will need to find the acceleration for the ball and the acceleration for the coffee filter. So for both of these, you'll get some value plus or minus some uncertainty. So you'll need to have two measurements formally written out like this. And then you need to create a whisker plot comparing the two. So you should have this against acceleration. And then you'll have just the 2 points with error bars. Are these 2 points consistent with each other?
Yes.
Yes, because those error bars overlap. If those error bars overlap, it means they're consistent with each other, and it means they could actually be the same point. You could then have measured the same acceleration for both the ball and the filter. Actually, that's not what I wanted to do. Are these 2 points consistent with each other?
No.
No. The error bars do not overlap, so they are not consistent. That means that they are two different, distinct points. It means they don't have the same acceleration. Are these 2 points consistent with each other?
No.
We don't know, right? Yeah, no, it's hard to say. Because they both have the same endpoint, we actually can't say if they're consistent or not. If this is the case, then we would want to take more data. It's unlikely that you'll see exactly this case on your plot. It's just good practice to go over. Okay. Are there questions about what we've gone over? So just to summarize again, we used our kinematics equation. We changed some stuff and we set our initial velocity equal to 0. And we got this equation of displacement is equal to 1/2 AT squared. We used an equation of a line like we do. And we're able to find that acceleration is just equal to 2 times our slope, which gives us the value for acceleration. But to get that uncertainty, we have to use that min-max method. And that you will have 2 final accelerations reported, one for the ball and one for the filter. And you'll need to have a whisker plot that compares the two to each other. This isn't what you're doing today. This is what you'll do for that 3rd week, that conclusion week and analysis. And I will go over it next week, and I will go over it that 3rd week too. So it's okay if you don't quite understand all of this today. So again, we have this broken down into 3 weeks. This week you're designing the method. One will be for the real world situation and one will be for the simulator. Work as a group. You can come up with your objective and your prediction as well. Next week, you will be doing the data collection. You are going to collect a lot of data points. So almost probably about 200 measurements. And then the 3rd week, you will work on those conclusions and those analyses. So remember, you have 3 plots, 2 displacement versus time squared, and then 1 whisker plot. Are there questions about this? All right. So again, these are the simulators. You don't have to work in them today, but it's very helpful, I think, to kind of go through them so you have a better understanding of how to write your method. You're just going to be comparing, the ball and the coffee filter's accelerations. You calculate them again by dropping them from different heights. So as a group, you'll decide which heights you want to use. You'll drop them several times from each height because that's how we get our standard deviation. You're going to use your own timer, so not either of these. These plots are wrong. You'll do it for both the coffee filter and the ball. Again, picking whichever heights you want to use. All right, are there any questions at all?
Yes.
Yes, what's your question?
So are we dropping the ball and the coffee filter from different height or just same height?
You'll drop them from different heights. So maybe you pick 10 different heights to use for the ball.
Yeah.
So maybe it's, 0.1 meters, 0.2 meters, 0.3 meters. You'll do it from
Okay.
each of those heights, but you'll do it multiple times from each height, because just like in the past, we want to be able to use the standard deviation at those
Okay.
heights.
Yeah. Okay. Thank you.
Are there any other questions? Okay, give me just 1 minute to finish setting up your breakout rooms. Okay, so this is all we're going to be working on for the rest of class, is just these methods, designing your experiment. I will be around a little bit if anyone has any questions, but if you need me sooner, please just pull me into your room.